Thank you, and thanks everyone for coming. It's good to see so many of you here. I'm going to be talking about a library I've been working on recently called Magnolia. The talk is going to be in three parts, of which one part won't exist because it's normally a 90-minute talk and I'm squeezing it into 20. So I'm going to start off by talking about very fast about generic derivation in Scala, what that is. I'm then going to introduce Magnolia, which is a macro for generic derivation, and I'm not going to tell you how it works. So I've tried to summarize what generic derivation is. It allows us to generate type class instances for types we don't know beforehand, composed from type class instances we have. Type class instances that exist in implicit scope. It's probably worth me asking a question to the audience. How many of you here have used a library which provides generically derived type classes? So I'd say more than half, probably 60%. How many of you have written your own derivations with, I presume with Shapeless for your own type classes? Okay, so probably close to 10%. Okay, that's a good indication for maybe how hard it is. So I'm going to use a very simple example, a show type class throughout this. So I'll quickly tell you what this does. I'm sure you all know. A show type class will basically convert a specific type into a string. You give it a type, it gives you a string representing that type. And we would use it by implicitly getting that instance. So we would get the instance for example, a show of int. We would call show on it, passing it the thing we want to show, which is an integer, and it will give us a string. It's incredibly boring, but it serves as a useful example for this talk. Now, if we wanted to manually derive a type class for a case class, say, we would write something like this. Here's the show type class. Here are some type classes written actually with SAM types, but these are sort of our primitive type class instances. And we want to compose these into a type class instance of show for a person. And the way we might do that is we define the implicit. We construct a new, you can also do the pointer. We construct a new show of person, and we implement our show method with this string here, which uses the string show instance. It uses the int show instance, which it gets from up here, and it just calls show, passing them the parameter components of that case class. Joins them all together, puts them in a string, prefixes it with the word person. What is this? This is... That has never happened before. I hope it doesn't happen again. I'm scared now. Okay, let's concentrate. So we have our new instance of show for a person. Likewise, if we had a co-product type, which in Scala there are seal traits as a convenient representation of these, what we essentially want to do is use instances of these type classes for the components of that seal trait, the components of the co-product, and basically delegate to them. So an implementation might look at an entity, which is the supertype, the seal trait. Based on its type, whether it's a person or an organization, we delegate the task of showing to either that show person we created on the previous slide, or some other one we might create for an organization case class. So it looks a little bit boilerplate. The most interesting one was the product case, but nothing particularly complicated. But this is a very simple ADT we're doing this for, and you can imagine that for many of these, which may be deeply nested and recursive, the complexity is greater and greater, and the actual code, which is very boilerplatey, the actual code you need to write gets quite large. So, I'm just going to make it a bit brighter for myself. There we are. So in a world where we have generic derivation, what we might do instead is import some sort of generic derivation implicit with this line here, and then we would just be able to request, with no more information than we have above here, just these primitive cases, we would be able to automatically derive an entity for show without any extra code in our source. That's what we're aiming for. And Magnolia is my attempt to provide this. So it is basically just a macro. It's a larger macro than the macros in Shapeless, but it allows typeclass authors and users to easily write fast and debuggable generic derivations for arbitrary typeclasses. So I've italicized 3 words here: easily, fast, and debuggable. These are 3 key things I wanted to improve on the state of the art. So a bit of background. It's about 400 lines of code. It's not a huge macro. Code's pretty dense, but it's not enormous. It's open source licensed under Apache 2. It supports a variety of different typeclass shapes and different structures we might want to derive for. It's early days. It needs more real-world testing. I've only done simple examples so far. Version 0.61 was released this morning with a bug fix, but there are people using it, and the feedback has been exclusively positive so far, I'm happy to say. Probably people just don't tell me if it doesn't work, but I would like to know if you try it and something doesn't work as expected. The website is magnolia.work, and there's also quite a comprehensive tutorial if you have your own type class you want to derive for. But I'm going to give you just a quick overview of how it would work and what you can do. So I've already told you about seal traits and case classes. It will also work for case objects, which are a little bit like case classes with no parameters. It works for value classes, which are a little bit like case classes with a single parameter, and tuples, which are like generic case classes with no prefix. So the top case is the co-product case. The bottom 4 are product cases, and it'll do all of these, and you can actually disambiguate between them with the API if you want to. But we observe that there's no standard way to combine arbitrary type class instances. A number of shows corresponding to each parameter in a case class will combine in a very different way from a number of equal or eq type classes. We work differently with each one. So we need to provide some specification to the macro so it knows how to do the combinations to construct the type class instances. Magnolia's API aims to be flexible enough to deal with the vast majority of type class shapes and structures, while also not being too complicated and being easy to use. And that interface, I put interface in quotes because it's not an interface in the object-oriented sense. It is basically a list of methods that need to exist in some form on an object for Magnolia to be able to do a derivation. They are a type constructor for defining what the type of the type class is and which parameter in that type class is generic, which one we are genericizing with the macro. A method which defines how we do the combinations, how we bring together the type classes from different parameters into a new type class instance. A method for choosing which type class we delegate to, in the case of seal traits, and a very boilerplate method for binding to or invoking the macro. That's a one-liner in I think every case. This is the type class, so the type constructor you need to write. Very simple. It's called type class. It will always take one parameter, and it will be equal to the type class you want to generate. If your type class has more than one parameter, then you would have the other parameter in here, but fixed to some value. So this enables you to specify effectively which parameter is going to be the generic one. For show, it's pretty trivial. And then this is how we write this is how we define the combinations. And I'll spend a little bit longer on this slide. Don't worry if you don't understand the detail of what I explain. The main takeaway point is this is a sort of representative size of implementation for a combination. So you can see that we can see the definition here. It returns a new instance of the type class parameterized on T, which is completely abstract. We don't know anything about it. So any references to T have to be written in a way which assumes very little about them. We do know that we are deriving for show. You can see show appearing in the parameters here. And we implement the show method, the abstract method in the show type class. And the way we're going to do it is we're going to take the parameters of the case class. Now, the case class is passed by the macro as a parameter to this method, to the combine method. And it's sort of a lifted representation of a case class. It gives us access to the parameters. Here are the parameters. They're param typed on show and the abstract type T. And for each parameter, we're going to create a string. And with that string, we're going to join them all together with make string, use the name of the type, which is simply the case class object dot type name, put some commas between them. And the interesting bit is really this line here. Now remember I said we know very little about the type T. We know even less about the type of each parameter in there. We don't know whether it's in real life or at runtime, whether it's going to be a string or an int. So we have to write without knowing that. And sure, we can get a label. We can get the name of the parameter. And that's always going to be a string. Nothing complicated there. But we also have access to the type class. That is the show type class corresponding to that parameter that Magnolia will find for us. We don't worry about how it finds it at this point. But we assume that it will either find one or it will be recursing and will generate it for us. And with that type class, we're calling show on it because we do know that it's a show. We know that much. We pass it a dereferenced T. Now T is unknown, T is abstract, but it's a case class. We have a way of dereferencing the parameter inside that case class. So we have access to that parameter. The type here is actually p.type. It is a type that is existentially quantified on the type P. Now that's a complex type. We don't want that type hanging around for too long. So what we do is we pass it to a type class of show, which is also parameterized on the same type. That complexity cancels itself. They cancel each other out, and we end up with a string. So this is a string. All is good. And that will be type safe. You can't just put any value in there. In fact, by parametricity, the only way of combining these is the one I've shown here. And join them all together, we get a string. So that is our implementation for a show type class for combine. Obviously, it'll be very different for different types you might be producing. And what the macro will do is it will simply call that combine method, passing it a case class instance. I've sort of prefixed this with $, to indicate that it's magically generated. The macro will do that. It will pass it to the combine method, and it will give us this type class result. So that's the code we write. The code in the brighter code at the bottom is the code the macro will generate. In the case of seal traits, very similar thing. We have a convenient method, dispatch, which will dispatch to a subtype. I won't spend too long on that, but again, look at the size of the code. It's small. It's reasonably simple. I'll take questions at the end, usually. So we put all these into an object, derivation object, which I'm calling show derivation, and we additionally include an implicit method, which I'm calling gen, which references the macro. Because this is defined on this object, it knows where to find these methods. So show is what I would call a contravariant type class. The generic parameter t is an input to the show method. And the same is true of something like eq. These two will have a similar structure in the implementation, but we can also support cases where we are producing a result, where we're producing an instance of the type T. Default will return a default value for a particular type, or a decoder, which is, I'd call these covariant type classes. Decoder, you actually need to produce a new instance of a case class in implementing the abstract method in your type class. So there are ways to do this with the API, which I won't show you. You can also get type classes which are parameterized on a higher kinded type, such as functor. We don't support this. The API doesn't have a way of writing it. I think it's possible, but I haven't spent long enough trying. So that is a feature for version 2. You might ask what happens when it fails. If you've used Shapeless and tried to derive for a type class and you just don't get a result back, you literally don't know where to look. You do searches through the structure. So if we had an ADT like this, we tried to get a show for entity. There's lots of types in here. If, for example, we didn't have a show of Boolean, we would get a sort of stack trace that looks like this. It points through the structure to telling us step by step all of the types it couldn't find and the ultimate reason at the leaf node why it couldn't. And we then go back and fix this. Maybe we get another stack trace on the second error we had, and we'd go and fix that. But there's not much work to be done in sort of any complicated searches. Recursive data types, these are supported. These work without any special magic on the user's part. You can see that if you're trying to generate a generic type, generically derive a type class for a tree, tree as a co-product has two branches, sort of two parts, leaf and branch, and the branch has tree within it. So if you were naively following an algorithm, it could potentially just recurse indefinitely and never produce any result. What Shapeless does, it has a thing called lazy, which deals with this. With Magnolia, we have a sort of greater knowledge at the point it's doing the derivation, and we can identify when we would have been recursing and simply point back to point back recursively to the derivation for that particular type. There is a story on implicit prioritization. I think we all probably know that it's quite complicated, the rules around it, but you often have a situation where you want certain implicit state priority over others, and Magnolia has a story on this. The jury is still out, I think, on whether it is the right story, but it's, I think, maybe easier to reason about. The Magnolia implicit works like any other implicit. It gets called at the same priority it would as if it were a non-macro implicit. That works, hopefully, as you would expect. But for any recursive call to Magnolia, so when it's deriving a nested case class, for example, that will be beaten by the existence of any other implicit that's in scope, even in companion objects, even if they would have had a lower priority than the Magnolia definition. That gives you what I think is a sensible default, and there are ways that are quite easy of overriding that. Whether it handles all cases, I don't know, but I've got some ideas on how it could be tweaked. Just to mention, we also support GADTs, and we also support recursive GADTs, which I think were a problem for Shapeless. It can do GADTs, Shapeless can do recursive types, but the intersection of these two was problematic. Now, compiler performance. I think this is something that a lot of people complain about with Shapeless, and the reason is it generates huge amounts of code. When it has an implicit that calls an implicit that calls another implicit, all of which are producing more and more code, there is a large amount that you just don't see at the use site that gets generated, and this is the reason why the code is so slow to compile. Magnolia does some deduplication. It's aware when it's doing the same thing twice and will reuse instances where possible. It also caches implicit searches in the same position for the same type, so it doesn't need to do that work repeatedly. And this is the results for one particular example. The three 3 lines up here. This is a cold JVM, and I repeatedly do the same compilation, I think about 25 times. They all improve as the JVM gets warmer. The top is Shapeless with kittens using deriving a show type class for some complex ADT I wrote 50 times in the same file. And the bottom lines are Magnolia. Magnolia ends up around 2 seconds for this particular example for the full compilation. Shapeless with kittens sort of, I think, ended up around 50 seconds, maybe a little bit faster. So it's quite a bit faster, but I mean, a lot of that is deduplication. It depends a bit on how many times you have the same type class being derived in the same file. My worst case scenario was 4 times faster, but it's somewhat arbitrary how I define my ADT as to what benchmarks I want to get. And the different lines are for different versions of the compiler. Type level Scala is actually quite a bit faster for both Magnolia and for Shapeless. It's this bottom line here and the bottom line there. Runtime performance, I've not looked at this in much detail, but you saw that we had instances of a lifted case class, lifted parameters. These are all objects which get created on the heap. This is garbage that is maybe worrisome if you have a lot of parameters. So I wanted to look at this. I've not tested it thoroughly, carefully, or even accurately, but I did try to construct 1 million show instances for a particular ADT, and it was 52 times faster than Shapeless, which got me excited. And then I actually tried to call show on that instance, and it was only twice as fast. So I think I'm aware there is garbage produced. If I'm twice as fast, and that's the best I can do, it's an improvement. It's maybe specific to show as well. So it depends on a lot of factors, but this is an area I'll be spending some more time on once we have version 1.0 released. So I'm hoping that can be done in the next 2 weeks. I'm not precious about 1.0 being perfect. If it's not, then version 2 comes out a bit later, and we'll move from there. So runtime performance is probably my next priority after that, and then looking into supporting higher kinded type parameters. And that is all I've got for the talk, because I'm already over time. But I'll be around outside later for anyone who wants to hear about details of the how it works behind the scenes. That's a longer conversation, but I'll be available. Please come and talk to me. And do I have time for a couple of quick questions now?
One very quick question.
A very quick question, okay. Who's got a quick question? Eugene, did you? No? So that was a long question. I bet it was going to be a long one. No one I guess nobody thinks their questions are, okay, go on then.
All right, so this dispatch method, right, that goes through the alternatives of the silk creator. Can we derive it as well?
You could derive it for the...
Can you go one slide back?
It's one that way, isn't it? There.
So
the implementation of this one would be almost identical in every contravariant case. So the only thing that would differ would really be this implementation, this call to show here. But it might take more than one parameter. So for eq, you would need to cast the first type parameter and the second type parameter. Sorry, the first value parameter and the second parameter. You'd also need to check that if your dispatch disambiguates based on one value. With the eq implementation, you need to check that the second value is of the same type. If it's the same type, then it's not equal, so false, return false. To quickly summarize, in some cases you could come up with a sensible implementation automatically. I haven't provided it because I don't know how common those cases are and how hard it is really to write just those 3 lines and just have a consistent way of doing it for every single case.
Thanks.
Okay, thanks. I'll be outside now.